You started recording?
Yeah, so today we have with us Maria Kazachenko from University of Colorado Boulder and NSO, and she's going to tell us something a bit more substantial and a bit more concrete and a bit more detailed than what I was telling you before. And if I'm not mistaken, we're going to have 2 lectures by Masha and then a hands-on exercise. So he will be with you next 3 classes. So before we start, I'm just going to pass one piece of information to you. I will be hanging out at this Zoom ID on Monday from noon until 2 p.m. So you can find me there if you want to discuss, if you want to ask me anything about the homework or any questions or something like that. I will also post your homework your next homework over the weekend. So yeah, I mean, I'm just going to be there if you have any questions regarding the course or solar physics or anything that we covered so far, or any logistics regarding grades and so on and so on. Yeah, so you feel free to drop by. Don't feel obliged to. If there is nobody there, I'm just gonna type something and read something and so on. So yeah, okay. Anyway, without further ado, Masha, thank you for being with us. Go ahead and everybody enjoy and ask questions as you would otherwise.
Yes, thank you very much, Ivan, and thank you very much for inviting me to tell you about my favorite field of solar physics, magnetic fields. So I'm Maria Kazachenko. I work here at the CU Boulder and National Solar Observatory. The goal of my lecture today is to make you learn new things about magnetic fields. So since the goal is to learn, please don't be shy. Ask questions in person or using chat. And Ivan, if I miss anything on the chat, Ivan will let me know if there are any questions there. So today and 2 classes next week, we're going to talk about how to derive properties of magnetic fields in solar photosphere. And I'm going to use Cursor here to tell you what I'm going to talk about. And here on the bottom, we see an example of photospheric line of sight magnetic field observed by Solar Dynamics Observatory. Okay, so let's start. Where's my cursor? I lost it. Okay, next slide. So why do we care about magnetic fields? Here is an example of a beautiful movie of an eruption observed by AIA instrument on board of Solar Dynamics Observatory. Why do we care about magnetic fields? Because knowledge of coronal magnetic fields is vital for understanding long and short-term evolution of solar corona. Okay, so things like we see in here, for example, a solar eruption, we could get much more information and much more understanding of what's going during eruption like this if we have measurements of the magnetic fields. Okay, so the question I'm going to ask during these 2 classes is the following. Can we use magnetic fields measured in the photosphere to understand the magnetic properties of solar activity? Very simple and at the same time very complex question. And to answer this question, basically, how can we use measurements to understand magnetic fields? We're going to do the following. During next 3 classes, we will go over methods that are used to derive some useful properties of evolving magnetic fields. And what are these useful properties? These are velocity and electric fields. And from these, you could actually get a bunch of others, including energy and holistic fluxes. So we assume we have magnetic field measurements. How do you get this? Jana and Ivan and Kevin, they already told you that it's a nightmare. But if you assume that you have these magnetic field measurements, the question is, how do you use these measurements to get more information about the properties of the solar corona magnetically? So here is the outline for next 3 classes. Today, there will be a lecture. Tuesday will be another lecture. And then Thursday will be hands-on activity. Today, we're going to talk about magnetic fields in the photosphere, okay? We're going to talk about early methods to find magnetic field flows. So once you have magnetic fields, how do you get flows out of it? By flow, I mean velocity and electric fields. Then next Tuesday, I'm going to go over the same topic, but at slightly higher level. I'm going to talk about modern methods used to derive these velocity fields in the solar photosphere. And these recent methods are listed here. including PDFI, Day4VM, and then some machine learning methods that people are actively working now on at NSO. And then I'll show you some examples of application of these methods to solar data, okay? And then next Thursday, most exciting part, is we're going to do some real stuff with our hands and brain. We're going to apply a specific, very simple method called FLCT to a sequence of HMI SDO magnetograms to derive some properties of the magnetic fields in the active regions ourselves. Okay, sounds good? So that's the plan. Here is again the plan for today. We're going to slowly start thinking about magnetic fields and why do we care about magnetic fields. So the first thing I would want you to ask is why magnetic fields on the sun are important. Why do we care? Then I will talk where can we presently routinely measure magnetic fields on the sun. We know that it's a hard problem and we cannot measure magnetic fields wherever we want. Then I will talk about the physical properties that we could get once we know magnetic fields, and there are a bunch of them. And you'll help me to think about this question as well. And then finally, I will tell you how can we use magnetic fields along with tracking methods to derive velocities in the solar photosphere. So I'm going to talk about early methods from around 15 to 10 years ago for tracking magnetic fields. And specifically, I'm going to talk about two groups of methods, tracking and inductive methods. Okay, so that's the plan. So before we start talking about the details of deriving flows, let's ask ourselves why magnetic fields are important. I know it's a basic question, but since in this course you haven't talked about magnetic fields much, I want to make it clear in your heads why do we care about magnetic fields. And here is a plot that many of you have already probably seen, which is plasma beta versus height of solar atmosphere. So here we have, on the x-axis, we have plasma beta, which is basically kT divided by B squared, and kT is the, what is it? Gas pressure, and ideal gas pressure. B squared is magnetic pressure, so beta basically tells you about what matters, whether gas pressure matters or the magnetic pressure matters. And here is the height above the solar photosphere. Here's the photosphere, and we see beta varying from 10 minus 4 to 10 to the 2, shown in here as you go from below the photosphere to the chromosphere, to the corona, and to the solar wind. So what do you see? For the photosphere, below the photosphere, there is large fraction of plasma which has beta larger than 1, meaning that magnetic field is not important. However, once you cross the photosphere, you see we're mostly in this blue region meaning that we're mostly in the region where magnetic field matters. So in other words, magnetic field is really important above the photosphere, and by understanding how magnetic fields flow, how magnetic fields move, you could understand where is the plasma, what is the motion of the plasma. And here is just a summary. In the upper corona, gas flows drag magnetic fields. Okay, so that's this small region here, but that's solar wind. That's really above the photosphere. Then the region where we are mostly interested, if we are interested, for example, in quiet sun activity or active regions, is this region, lower corona, chromosphere, photosphere. In this region, magnetic fields drag gas flows. So magnetic fields, they really dominate. And then below the photosphere, it's the opposite. Gas flows drag magnetic fields. So to summarize, if we understand how magnetic fields evolve in solar photosphere and above, we will improve our understanding of how plasma moves. Very important, okay? Here's another illustration of importance of magnetic fields. Here I'm trying to ask and answer the question, where does CME, coronal mass ejection, and flare energy come from? And here is an illustration from a paper by Terry Forbes in 2000, very old paper. And here what we're estimating the energy requirements for moderately large CME. So how much energy do we need to energize coronal mass ejection? Kinetic energy, 10 to the 32 ergs. Heating and radiation, typically released in CME, 10 to the 32 ergs. Work done against gravity, 10 to the 31 ergs. Volume involved, 10 to the 30. We take the sum of all different parts of energies, all different fractions of energy divided by the volume, and here is the energy density that we derive that is necessary to produce a fairly large CME. So it's about 100 ergs per centimeter cube is the energy density that we need for the fairly large CME. Now the next question, where could this energy be supplied from? It's 100 ergs per centimeter cube. And here is a totally different view on this problem. We're just estimating what are the coronal energy sources, typical coronal energy sources. Here is kinetic energy in the corona. We estimated using just this simplified approach. Typical density, 10 to the 9th. Typical velocity in the corona, in the lower corona. And then if we just multiply all of these, we get energy density. Kinetic energy is 10 minus 5, much less than 100. Thermal energy, NKT. Take coronal values, 0.1, still very small. Gravitational energy, mgh. Another estimate, 0.5, so still very small. Now magnetic energy, here's the winner, b squared over 8 pi. B is about 100 Gauss in the corona, a bit even too high, but you get an energy density of 400. So what does it mean? It means that the major source of energy of solar activity, for example, during CMEs, is the magnetic energy. So the magnetic energy is absolutely crucial to, and the structure of magnetic field is absolutely crucial to understand what's going on in solar corona, okay? And to summarize, if we understand how magnetic fields evolve in solar photosphere and above, we will improve our understanding of flares and CMEs, okay? Here's another look at the same problem, why magnetic fields are important. As I said, all solar activity active regions and the quiet sun reflects evolution of magnetic fields. Magnetic fields observed in the photosphere, on the other hand side, are generated in the sun's interior, extending into the photosphere and the atmosphere. We cannot observe directly the magnetic fields in the interior. However, if we measure and understand how magnetic fields behave where we could observe them, meaning the photosphere, for now, we might get a better understanding of what's going on below the photosphere in the interior. In the same way, we cannot directly observe magnetic fields in the corona for now, so measurements in the photosphere, they provide us insight of magnetic field in the corona. And also they provide us with understanding of how magnetic energy is stored and released in solar atmosphere, okay? So let's now try to remind ourselves, where can we measure magnetic fields on the sun as of now? As of now, we have primarily most of the measurements of the magnetic fields in the photosphere. And what are these measurements? We have both line of sight, meaning the magnetic fields towards us, just one component. And also, since about 10 years ago, we're lucky to have vector magnetic fields measurements routinely. And what are these measurements? Solar Dynamics Observatory allows us to, Solar Dynamics Observatory has been launched in 2010, and since then it has been routinely measuring magnetic fields, full vector of magnetic fields in the full disk with a very high temporal resolution of 135 seconds, about 2 minutes, and quite high spatial resolution, okay? So what can I say about SDO? SDO is an excellent instrument, and the main reason for that is that it measures the magnetic fields at fairly high, vector magnetic fields at fairly high spatial resolution and temporal resolution, and it also measures what's going on in the sun, in the whole sun, using full disk. So what does it mean for us? It observes full disk. It means that we could understand long-term evolution of magnetic fields in the active regions, okay? So these are the advantages of SDO. Now, what are the disadvantages of SDO? These are the following. The custom version currently used in SDO is not very suitable for quiet sun. So if you're interested in what's going on in the quiet sun, don't use HMI vector magnetograms. Other problem, as you might have heard, SDO has some problems with contamination of signal due to the orbital motion. So if you look at long-term evolution of magnetic fields, you might see that there are some blue shifts and red shifts, so there are some fluctuations in long-term evolution. Doesn't mean that you cannot observe active regions on the long time scales. It just means that it's more complicated, okay? And you should keep it in mind, okay? And also for the short-term study, this effect is not significant, but it might play a role in the long-term studies. So SDO, I would say, is the flagship of vector magnetic field measurements on the sun, especially for long-term active region evolution. Then there is HINODE, which also routinely observes the sun since 2006, so already 14 years, hard to believe. SDO is different, HINODE is different from SDO in this way. It has a limited field of view. It doesn't observe the whole sun, so it only observes smaller patches that could cover the entire active region though. But the resolution here is significantly higher. So you have higher cadence, 30 seconds, and also higher spatial resolution. So the amazing movies that you might have seen with rotating sunspots and all sorts of small scale dynamics is probably from HINODE, a Japanese satellite, okay? And as I said, the advantage is the high resolution here. The disadvantage is the limited field of view. Then we have other non-routine measurements. And here I just wanted to mention Sunrise. IMAX mission launched in 2009, which was a balloon. This is kind of once in a lifetime experience. It was just a balloon that measured magnetic fields for a short period of time. However, with extremely high cadence, 10 to the 40 seconds, and resolution, spatial resolution, 40 kilometers, okay? The advantage of these types of measurements is that we get a new kind of peak on the sun with ultra high resolution, but very short period of time, okay? So this is the story about the photosphere. How about everything above it? In the chromosphere, I'm not even going to talk about it. It's extremely hard as of now to derive magnetic field measurements. DKIST will be the first major effort in this direction. There have been some ground-based efforts, but I'm not an expert in this field. And also, I would say that if we're talking about routine measurements, there are very few available. And then the solar corona, again, the same story. It's extremely hard to measure vector magnetic fields or even line of sight magnetic fields in the solar corona. What we have had for now was of limited spatial resolution and very limited temporal cadence, although there have been some efforts in this direction, okay? And to summarize, the only routine magnetic field measurements we have so far, and here I'm talking about more higher temporal cadence measurements, not ground-based like daily measurements like we would have from peak observations. So if we're talking about routine high-resolution measurements, there are basically two instruments from which you could get magnetic fields: the Solar Dynamics Observatory full disk and high-resolution HINODE, okay, with high resolution and limited field of view. So that's the story of the source of magnetic field measurements. And to summarize, we have decent measurements of magnetic fields in the photosphere, but not in the chromosphere and the corona, okay? And DKIST, with DKIST, the story will change completely. You have already seen this table, most likely with Jana. So just to summarize, so it's overwhelming table, I'm not going to scare it, but here's the take-home message. Magnetic fields from DKIST. We are going to get magnetic fields on DKIST on disk in the photosphere and the chromosphere, and the resolution here will be almost 10 times higher. Will be amazing. On the limb, we will get the coronal measurements with a resolution of about 300 kilometers, hopefully. What are the advantages and disadvantages of future DKIST measurements? We will get super high temporal and spatial resolution, something that has never been seen before. We will get magnetic fields not just in the photosphere, as we have already been capable of analyzing, but also in the chromosphere and the corona. So these are completely new chapters of solar physics. And to summarize, it will be revolutionary new science just because of the new instrumentation and new approaches available from an instrumentational point of view. What are the disadvantages? Yes, somebody is having a question, or there was
I just wanted to add that also we usually think about these two regimes, but there is also this intermediate regime where we will be able to observe prominences and filaments, which are something in between. So most likely they are somewhere in the transition region, and also we will be able to infer their magnetic fields.
Sure.
So we will try to squeeze one lecture about this until the end of the course, or maybe Steve will talk about it.
Oh, wonderful. Okay, that's great. Okay, yes, and I want to mention that here the view that I'm providing is highly simplified, of course. First of all, the photosphere is a constant tau, constant optical depth layer. It's not a constant height layer. So it's sometimes even confusing to talk about photosphere versus chromosphere transition region. But if you look at it in a very simple term, you could think of it as a zero approach. In this framework. Thank you, Ivan. What are the disadvantages? The disadvantage of DKIST is that it will have a limited field of view. Okay, so if you're thinking of tracking active region for many days by looking at the whole active region, it's not realistic, okay? Because you would need to really scan a large field of view. So high resolution always means that you are dealing with a smaller field of view. Then you would also have to deal with limited duration compared to space-based observation, because we're living on the Earth. And so you could deal with maximum of 6 hours at best length of observation. So you should think of something most likely small and dynamic, or large and not very dynamic, or flares, yes. But most likely you should focus on the smaller kind of events. And then, as you have heard before from Jana and Kevin and Ivan, with DKIST, you would have to deal with complex inversion, where for SDO, most of the time you have to ignore the inversion problem and just rely on what you have already. And in Hinode, you could ask to tune it somehow, but you don't have to deal with it yourself, okay? So this is the story of how DKIST fits in here, okay? So now I'm going to show you some examples of present-day magnetic field measurements. First, I'm going to show you measurements from HMI SDO, and then, so the space-based instruments, and then the highest resolution IMAX sunrise. And here is an image of SDO, an illustration, I would say. And then here is an image of sunrise. So let's look first at SDO. Here we're looking at the photospheric magnetic fields in an active region observed not by SDO, by ground-based line-of-sight magnetograph from Gong on Canary Islands on 14th of February 2011, okay? And what do we see here? We see some active region. The resolution is not very high. Okay, let's now look at the same active region 3 days before, and you see that there is nothing, okay? So 3 days before, there was nothing in the place of this active region. Now, if you're on the ground, you cannot really understand what's going on because you are limited with day and night, okay? Yeah. However, if you are in space and you're using a mission like SDO, you could actually observe the same active region as it emerges on the surface of the disk. And here is not an animation, here are observations of vector photospheric magnetic fields in this active region from HMI SDO. And HMI stands for Helioseismic and Magnetic Imager, SDO for Solar Dynamics Observatory, okay? So what do we see here? We see in red, we see positive magnetic field, the vertical magnetic field. In blue, you have negative magnetic field. The arrows show you orientation of the horizontal magnetic field, okay? And what we see here, we see basically here what we've seen before. In the beginning, there is no active region, then there is an active region. You observe emergence of an active region on the surface of the sun. And you observe this emergence happening during several days. And along with this emergence, you see all kind of very interesting dynamics, okay? So that's the dynamics you see here. Emergence. Let's look at it without me speaking too much. So very, very, very active emergence in here happening. And then there is lots of shearing happening in here, okay? Okay, so all sorts of interesting dynamics going on during these 3 days of active region, or 5 days of active region evolution. And these are all vector magnetic fields, okay? So strong emergence here. So just to summarize, magnetic fields at active region scale. If you've never seen an active region magnetogram before and you've seen this movie for the first time, what have you learned from just watching this movie? You've learned that this magnetic field is highly dynamical. It emerges, it cancels, it rotates, it shears. And what you should know is that all these dynamics contribute into storage of magnetic energy in the coronal magnetic field that leads to solar eruptions, an aspect that I'm particularly interested in. So by looking at what's going on at the photosphere with this kind of measurements, we could learn more about active region magnetic fields higher up above. And as we know, the coronal magnetic fields are not available. So looking at the photosphere could really help us discover what's going on above where we have no other measurements, okay? Now we're going to switch gears from the active regions to the quiet sun. And here are observations in the photosphere of magnetic fields in the quiet sun from a balloon called sunrise, okay? And we will see here a sequence of 30 minutes. Here is a continuum image, the Doppler velocity, line of sight magnetic fields, and transverse magnetic field, okay? During these 30 minutes. So this is a teeny tiny portion of the sun and the evolution of the magnetic fields in this tiny portion during 30 minutes, okay? So before, by the way, we only had 3 frames with SDO during this 30 minutes. Now we have a whole sequence of images in the quiet sun. And even during this 30-minute sequence, we see that there is lots of things going on, okay? So you see that there is lots of cancellation, emergence, shearing. So same kind of story, but now at the smaller scales. Okay. So lots of things going on. So if you've never seen magnetic field measurements of the quiet sun before, what can you say from these movies? You could say that quiet sun magnetic field is highly dynamical. There is emergence, there is cancellation. There is lots of rotation and shear. And all these dynamics contributes into storage of magnetic energy above on the smaller scales. And the big question that we want to understand is, how is this motion related to coronal heating? And this question still haven't been fully understood. Okay. Okay, so imagine we measure magnetic fields B, vector magnetic field at the photosphere. Okay, so we have vector 3 components of the magnetic field, Bx, By, Bz, as a function of longitude and latitude. What physical properties can we derive from B at this layer? So that's a question for you. I want you to help me think and also wake up after lunch. I'll give you a minute to let's leave your answers in the Zoom chat. What physical quantities can we derive from one layer of magnetic field measurements? And now it's 2:31, so I'll just stop in 1 minute. I'll start talking in 1 minute. So just type your answers in the chat. This will be our version of Clipper. Yeah, think Maxwell's equations. Everything you learned in E&M. What can you get from vector B in one layer? Yes, more. Very good. Yeah, you could think even about the most basic properties. Very good. How about the active region description? How do you describe an active region? Okay, 20 seconds left. Yeah, very good answers. Okay, very well. Okay, so some answers here. Curls, electric currents. Very good, exactly. Magnetic energy. Yes, in a simplified form, B squared could give you an idea of magnetic energy. Magnetic field geometry. Yes, very good. You could get magnetic field topology from the magnetic fields. Coronal vortices. With some form of magnetic field extrapolation above, you could indeed get shape of the coronal magnetic field and coronal vortices. Connectivity again from the extrapolation. Electric fields from dB/dt. Very good. Yes, that's the topic of today's class. Very good. So thank you, everybody. So the first thing, the simplest thing nobody thought of is the magnetic flux. So we could get how much magnetic field in total participates, for example, in an active region. If you integrate magnetic fields over the field of U, and here is an example of vector magnetic fields observed by HMI on SDO. Positive, white, negative, black magnetic fields, blue, horizontal, and red horizontal magnetic fields corresponding to magnetic field BZ below. So here is, you have horizontal field going this way and then this way, okay? So you have these measurements, you could get magnetic flux, the simplest description of how much positive and negative magnetic field there is, or unsigned magnetic flux listed here. It gives you an idea of how large an active region is. Or also it could give you an idea of, for example, what's the change of magnetic flux, the rate, magnetic flux rate, the recirculation of magnetic field in the quiet sun is. So another very important property. So you could take derivative of it and get the flux rate in the quiet zone in the active region. Then current density, very good. We could get, by taking curl of horizontal magnetic field BH, we could get vertical currents in each pixel here, okay? And you could actually do this exercise next Thursday. What does current tell us about? Current tells us about how much free magnetic energy there is in the magnetic field stored above, or in other words, how twisted the magnetic field is above. It has something to do with eruptivity potential of, or with capability of magnetic fields to erupt. So an extremely important measure, okay? And as you see, you could only get it from horizontal magnetic field. So if you're dealing with line of sight, and if you're using line of sight for extrapolation, forget about the currents. Now that we could also get vector potential. That seems like a very non-useful property, however, very useful for several other useful properties that I'm going to define in a second. Vector potential is just taking curl of potential parts of the magnetic field. Then you could also get the electric field, as Jonathan has mentioned. You could measure magnetic field vector change, dB dt, and then it's related by Faraday's law with E. So if there is some way to uncurl this equation, then you could get E, okay? What else? Magnetic energy flux, E cross B. If you know E from here and you could get it from B, then you can get magnetic energy flux. How much magnetic energy goes through the photosphere? Why do we care about magnetic energy flux? As I have shown you for CME flare energy balance, it's the magnetic energy that defines it all, okay? Helicity flux, another extremely useful property. By taking AP, the vector potential, curled into E, and then integrating over the surface, you could get how much helicity flux is going through the photosphere. What is helicity? Helicity basically tells us how much shear and twisting there is in the field. Something also extremely important for understanding all kind of aspects of solar activity. Then there is also magnetic shear. Basically, it tells us how non-potential field is. So what's the angle between potential and non-potential field? You could also derive it from B vector. There is also Lorentz force that you could find. So lots of very useful properties, but just looking at and analyzing the three components of the vector magnetic field, okay? The hardest variable to derive here is, as you might have guessed, is electric field, because you need to uncurl this equation. And if you uncurl something, then you always have to deal with scalar potentials, okay? And so the next two classes, we're going to basically talk about how to uncurl this equation, okay? Because once you know E, you could get magnetic energy and helicity flux, okay? And as I said, for energy helicity fluxes, we need to know electric fields, okay? Now, reminding ourselves, not in terms of variables, but what else can we get from magnetic field vector? Magnetic fields at the photosphere could be used to improve forecasting of solar flares. Magnetic fields at the photosphere could be used to find magnetic fields above in the corona by using some kind of extrapolations. And here is just restating the fact that we don't have measurements in the corona. We could use potential field extrapolations using magnetic field measurements here. We could use nonlinear force-free extrapolations. That's a whole another topic. We could use data-driven simulations to model the field above. And since I'm involved in the data-driven simulation, I just want to show you an example of coronal magnetic field. This is a result of simulations that you could get from the vector magnetic field measurements. Top view and side view of synthetic coronal brightness shown in red. So basically here you're looking at artificial AIA or artificial emission of the active region, same active region I've shown before, as it emerges on the solar surface. Okay, so even by having just one layer of measurements, you could get a lot of ideas about what's the evolution of the coronal field above. Okay. So as I said, the hardest variable to derive from all of this is electric fields. So now I'm going to talk about the electric fields. So finding electric fields is very hard. Why is it hard? Well, the most natural and the earliest way to derive electric fields is to just use direct measurements in the same way we use direct measurements of the magnetic field. And with electric fields, you might think that there is a Stark effect that might tell us about the electric fields from spectral measurements, and it turns out it's extremely hard to do that. For that reason, all the electric fields we derive now are derived from magnetic fields. So now I'm going to talk about the approaches to find electric fields from magnetic fields. One approach to find electric field is from the velocity field, horizontal velocity, okay? And the main idea here is that we assume that we're dealing with ideal MHD, meaning the electric field is equal to minus V cross B. Okay, that's just definition of this assumption. If we know velocity field, then we know electric field. But then, how do you find the velocity field, V? Okay, so that's the question. And we're going to talk about it in more detail. Another approach is find E, not from V, but from uncurling the Faraday's law, shown in here. So how do we uncurl it? That's the question. So today I'm going to review the earliest electric field inversion methods. There are two groups of inversion methods here. The first group are called non-inductive or tracking approaches to find velocity field. So these tracking approaches, they have no physics included. They basically assume that we are finding correlation of moving paint, moving kind of features, correlation function, and we find velocity from maximum of these correlation functions. And the two most famous approaches here are the following: local correlation tracking and Fourier local correlation tracking. Now there is another group of electric field inversions, and these group of methods implement some form of physics. And in particular, these methods, they use induction equation, and they're called, therefore, inductive approaches. And here are some examples of these. I'm going to talk about these in more details, and that's the equation they use. And today I'm going to show you comparison of early methods in these two camps before we had routine vector magnetic field measurements. And these are mostly based on the paper of Brian Welsh, 2007. So let's talk first about the first camp of tracking approaches. Perhaps the first method in this group is the local correlation tracking method, described by November and Simon, 1988. They introduced local correlation tracking method in solar physics. And the main idea here is that you have two images of intensities or whatever you want, and you try to minimize the merit function to find the correlation, to find the relative displacement dx between two consecutive images, E1 and E2. In other words, you have two images and you try to find the correlation function that minimizes you try to find a displacement that maximizes the correlation function between the two images. Okay, and here is just a mathematical description, and the main idea here is that you're using an apodizing window, which is typically Gaussian, which weights pixel closer to pixel xi more heavily in the sum. But again, the idea is very simple. You try just to use correlation function to find displacement between two pixels at two consecutive times. Okay.
Masha, I have a question.
Yes.
So here you basically need to repeat this correlation once for every pixel of the image, yes, because each pixel will have its own velocity.
Right. Yes, and that's the reason why this method was not. It was the most cited one because it was the first method that suggested this idea, but computationally it was quite intensive. So for that reason, the second method, which is the Fourier local correlation tracking, was much more efficient. And in this approach, so they applied this approach to white light observations of solar granulation. An example shown below: continue an image in the quiet sun from Sac Peak Observatory to derive granular velocities. And on the right, we see an example of derived granular velocities. Okay, so this approach was successfully applied, and what the authors of the method, November and Simon, found, they found that solar mesogranulation and supergranulation flow happen on these spatial scales. And here is just a cut out from this derivation. They actually have in the paper a larger field of view where you could clearly see this kind of cells of flows. Okay, so these are the derived granular velocities. So this was the first method. And I think in November, he was actually director of the National Solar Observatory. early in the 80s or something. So that was a huh?
I don't think Larry November was a director.
Yeah. Or he was just working there. Ah, hey, Dana. Okay. The second method, okay, and then this method, the LCT method, was first applied to a larger data set by Zhongqiu Che in 2001. So that was, if I know correctly, the first application of LCT to MDI SOHO, which was a predecessor of HMI SDO observatory line of sight magnetograms. So at that time we didn't have vector measurements in space, so that was a method applied to line of sight magnetograms. And here we see an example of in white and black of line of sight magnetic fields, and in the black arrows they show us the vector potential AP, and on the right is the derived pattern of horizontal velocities derived with the LCT. Okay, so as you see, these are the two areas. So you could see the velocity is determined in the strong field regions. So why they're determined in the strong field regions? Because that's where the magnetic field measurements are above the noise threshold level. So everything below is basically noise, and you could actually see some kind of granular motion, some kind of noise in here. And this was, these were the measurements performed for 40 hours in this active region with a cadence of 96 minutes. So much coarser temporal resolution than we have from SDO now, and 720 kilometer spatial resolution. And here on the right is basically a summary of these spatial derivations. The first row is a magnetic flux over the whole active region, positive and negative. The second one is magnetic flux rate, so basically just the derivative of this top panel. And below is the injected helicity. Okay, what is helicity? Helicity is basically described here, and I introduced it a couple of slides ago. Basically, a function that represents how much shear and emergence you have at the photosphere. And you could, if you want, divide it into these two terms by distinguishing this vertical motion and horizontal motions in the photosphere. And the V here is actually the velocity determined from the LCT here. And in this paper, the authors, they only focused on the shear term. Why did they focus on the shear term? Because VZ is unknown, so they just assume that it's not important, or they just focused on the shear term. And they actually found that the helicity changed during this 40 hours of evolution in this form. So that's the first illustration of what you could get from magnetic field measurements, and it's not even a vector, it's line of sight magnetic field measurements. Okay. Then the second method in this group is the Fourier local correlation tracking method, FLCT. And Brian Welch described it very well in his 2004 paper. And here is the summary of this method. So FLCT method finds horizontal velocity Vxy by correlating subregions at two times. Here, 2 hours, they are 2 hours apart to find local shifts. And in the first step, we're basically just taking two images at two different times at each pixels xy and yi above a threshold, again, not to deal with any noise. Then at the second time step, we multiply each pixel by a Gaussian at each pixel xy, yi, shown in here. Then as a result of this, we get a strong signal close to the pixel and a very weak signal everywhere around. And then now we basically truncate and cross-correlate these two in Fourier space, okay? And in the fourth step, as a result, we get uh, delta x, which is the shift between these two pixels, which is basically an interpolated maximum of the correlation function. Okay, so again, it's based on the idea of maximizing of finding the shift with a maximum correlation function between the two images. Okay, and it performs very quick in the Fourier space. Okay. So just to summarize this first group of velocity inversions methods, so they're primarily LCT and FLCT methods here. And the main problem of these methods that I haven't yet mentioned is that the derived velocities are just based on this visual shift between the two images, and is not based on any physics. Specifically, it doesn't, for example, try to solve the Faraday's law listed below. Now, the second group of methods are called inductive methods. And these methods, they rely on induction equation. And the first inductive method, which I note as IM, was suggested perhaps by Kusana-san in 2002, who basically assumed an ideal induction equation of this form, dB dt is equal to minus curl E, it's ideal, so E is equal to V cross B, so you get this equation. And what they did is they used line of sight magnetic field observations and LCT method to first find the horizontal velocity. And then they used vector magnetic field measurements from a Japanese observatory, and they derived horizontal velocity together with this induction equation to find these VZ, the vertical velocity VZ, okay? So that was an interesting mix of both the LCT, local correlation tracking, and also the induction equation. So as a result, you get three components of the velocity that satisfy the induction equation. Okay. Now here is an example of the application of this first inductive method. And the reason I'm showing to you is so that you get familiar with how this type of measurements are usually applied with, for example, active regions. Here is an application of inductive method to active region observed 20 years ago, where again, BZ was from Soho, vector magnetic fields was from Japanese ground-based observatory. And the result was the full helicity flux, where we not only have the shear term that we've seen before, but we also have the emergence term. And we look at it during several days of active region evolution. Here we have Gauss X-ray flux for the full disk, describing the flare activity of the sun. Here we have positive and negative magnetic fluxes. Here we finally have this derived property, the emergence term of helicity, flux, and the shearing term, okay? And you see that they could be both positive and negative. Then you could actually add up helicity flux is actually dH dt, so you could sum it up cumulatively to get total magnetic helicity. And here is the emergence term that we've seen in here, and the total term, which is just the shear, the sum of two, okay? And then what also has been nicely done in this paper is that the authors, they went one step further, and they also used the derived velocity field to get the Poynting flux, the energy flux. And they derived here the two contributions of energy flux depending on the sign of the velocity field, I think. And here is just the energy flux. You could also integrate it as a function of time and get cumulative total energy, which includes both potential and non-potential energy, and you could just find the potential energy. So that was one of the first applications of measurements of the vector magnetic fields to find both the full helicity flux and also the energy flux using photospheric measurements. Okay. Okay, now there were much more methods in this group of models. One I just want to briefly mention, the inductive LCT method. Welsh, who introduced the Fourier local correlation tracking, tried to improve the method so that it becomes more physical. Because as I said, FLCT flows, they only approximately reproduced observed magnetic fields changes. So as an alternative, they suggested to use this decomposition of the magnetic fields, the Helmholtz decomposition of the magnetic fields. Then when you plug it into ideal equation, you could solve for these components, chi and psi, and as a result, find the horizontal velocity fields. Okay. And then later there were a bunch of other methods suggested. Just to mention a few, Longcope 2004 suggested a minimum energy fit that finds smallest plasma velocities that could be consistent with magnetograms and magnetic induction equation. And again, though all those methods are inductive methods, then Schack in 2006 suggested another method that found optical flows that was statistically consistent with both the induction equation and the affine velocity profile. Then Georgoulis and Labonte in 2006 suggested another method, also inductive, and that used electrostatic potential decomposition. And there is actually very nice reviews reviewing all those methods at that period of time. And today I'm just going to show you some of the comparison before in this paper in Welsh 2007 that compared all these methods to try to find the best one. So what they did in 2007, they actually used a simulation, an MHD simulation of a bipolar magnetic region rising through a convective medium. And what's the advantage of a simulation is that you don't have to guess the answer because the answer is known. So in this case, they knew what's the velocity field, what's the magnetic field. So they could pretend they don't know these and try to find the velocity field and then compare the simulation velocity field with the one you derive from your best or worst model. And this model was just, oh, what happened? And this model was perfectly conductive. Something has happened. This model was perfectly conductive. Apologies for that. Okay, here it is. Do you still see my screen?
Yeah, we do. Everything is okay, don't worry.
Yeah, okay, great. So this model was perfectly conductive, meaning that dB dt is equal to curl E. So you could apply all the formulas that I've shown before, okay? So what did they get from this comparison of all the different methods? Yes, somehow interesting. Okay. So I guess the validation test didn't work. I have to omit this slide. Okay. Okay, so basically, I'm going to omit the slide because somehow it crashes. Keynote. So here is a comparison of different methods using this test case. Here we're looking at vector correlation for varying cadence. The best correlation should have 1. And here are different methods. So here we have, for example, the FLCT method shown in dark blue. And then here is direction correlation for varying cadence. So how good was the direction of derived velocity fields? And in this case, all methods, they did okay or poorly, you could say. And Dave, this bluish kind of color, did slightly better. Now, how about other variables? Here is a comparison of different methods looking at electric field comparison, EX and EY. So gray is one component of electric fields, black is the other component of the electric field. The ideal reconstruction should have it close to the dashed line. And you see that depending on the methods, you have slightly better or worse representation or worse reconstruction, okay? And here is comparison of E cross B. So from velocity field, you get E cross B to get E, and you do E cross B to get the Poynting flux, how much magnetic energy propagates in the Z direction. And velocity, very poor. The inductive methods perform much better, okay? All they depend, okay? So here is a comparison of performance of FLCT, DAVE, ILCT, MAF, and IM, all these methods summary. For velocity reconstructions, all methods did poorly. Inductive method, FLCT, and MEF performed similarly. DAVE did slightly better, but overall the reconstruction was not perfect. The electric fields, they did all okay. And then energy and helicity fluxes, as you could see, basically all of them, except for ILCT and MEF, they did not very well. Okay, so this one, MEF, which was actually the Longkop's method, they did the best at that time. So the question is why that particular method was the best? Good question. Maybe that the assumption of the minimum velocity that was made there was the most suitable for this physically to this animicity test case. Again, it was just a test case, which wasn't necessarily representing what's going on in the sun. So which inversion should we use to get the horizontal velocities V or electric fields? That's the question that you should ask yourself. So most of the described methods that I introduced here, they only used one component of magnetic field, BER, or B line of sight, and one component, the normal component of the induction equation to find horizontal velocity, okay? Now with SDO, we have actually routine measurements of vector and Doppler velocity measurements. And so we could solve for a full vector equation using measurements of vector magnetic fields from, for example, SDO or from ZCast. And next time I'm going to show you some examples of methods that routinely use vector magnetic fields for inversions. I'm going to talk about DAVE for VM and PDFI, and also show some of the machine learning methods. So what did we learn today? Today we learned why magnetic fields on the sun are important. Hopefully I convinced you that they are extremely important. I also told you about where can we presently routinely measure magnetic fields on the sun. And currently we mostly measure routinely magnetic fields in the photosphere. And we have both line of sight and vector magnetic fields there. Magnetic field measurements in the chromosphere and the corona are extremely sparse for now, having very low spatial and temporal cadence. And then I also did a small exercise with you of what can we get from vector magnetic field measurements. And also I told you about how can we use this vector magnetic field measurements or line of sight magnetic field measurements to derive velocity fields or electric fields using two groups of methods, tracking and inductive methods. And next Tuesday, I will show you how to derive velocity fields in the solar photosphere using vector magnetic fields, using more recent methods, DAVE for VM, PDFI, and also some machine learning methods that are not so much physics-based, but nevertheless have interesting results. I will also show you some examples of where vector magnetic field data have been used successfully and what have we learned from these. And also next Thursday, we're actually going to do a hands-on activity applying FLCT methods to a sequence of HMI SDO magnetograms. So we're going to use 5 days of magnetogram sequences to discover what's going on with active region magnetic fields yourself, specifically horizontal velocity fluxes, helicity, and energy fluxes. And you could play with varying cadence, varying spatial resolution to learn to see yourself how much does it affect your properties. Any questions at this point? Oh, we still have some time.
Okay, I have a question.
Okay.
Actually, I have a lot of questions, so I would first give other people a chance to ask. Okay, if nobody's asking, then so the first question was about these tests done on the simulations. Yeah, this is something that is very important, and also on the inversion part, we also try to do them sometimes. And my question is, when people compare these methods, was it assumed that magnetic field is known? So magnetic field was just taken from the simulation, and then the electric field was reconstructed,
yes.
right?
So basically, yeah, in all these tests, we assume that magnetic fields are known.
Which means that in the real life, the situation is even worse because magnetic fields are retrieved by inversions,
Right.
so they might be off as well, and then our electric field reconstruction might be even more off,
But then
right?
the question is, how can you, if you know that your magnetic field has problems, how do you deal with it without relying on them?
Yeah, probably there is
Yeah, I mean,
no
in
way.
principle, probably
And
you
the other
could have
question
some
was,
kind of complex model where your magnetic fields would depend on your reconstruction, and then your electric fields would depend on both, right? Mm-hmm.
yes. Yeah, no, I mean, I'm just saying that in principle, people could even do tests which would involve
Right.
everything.
Yes.
So start from a cube and then simulate the
Right.
observations, and then first extract the magnetic field and then reconstruct the
Yeah.
electric field. So that is something that
I think it's a cool idea.
An end-to-end test.
Oh yeah, for sure. Yeah. I agree. Absolutely. I
Or
would
just
think it's
train a
a good
neural.
plan.
Oh, or just train a neural network to take like the spectropolarimetric measurements and spit out the answer.
That's your homework for the next week then.
But it strikes me then, if this is what you're applying your inversions to, the inversions don't take advantage of the fact that you already have a measurement, a magnetogram that was somehow interpreted 10 minutes ago, say. Wouldn't it make more sense to build that into the inversions as well, so you know that what you've got is a plasma that you already have of extremely good measurement of the magnetic field from some earlier time at that exact position? Because otherwise, I remember having this discussion, and the biggest issue was the 180-degree disambiguity resolution, and that seemed to be done every time step completely ab initio, right? There weren't any methods that we were using that would resolve that ambiguity based on what it was the last time step.
I mean, later in time, Brian Welch, he suggested this modification basically that keeps the memory of the previous time step so that you avoid sudden switches from one time step to another one.
Right.
Yeah.
Yeah, but those switches have a logic in themselves. So you know that you're going wrong with the parameter set up in the disambiguation if it does that. So it's not really suited to your fields.
Yeah, I think one of the problems there is that it would require you to simultaneously interpret the whole, and if we are used to 4D cubes, then this would be a 5D cube. So X, Y, lambda, Stokes parameters, and temperature, and time, right? So it would require you to interpret all these bunch of observations simultaneously, and I think people are very, very much afraid of doing that. We can't even do regular spectropolarimetric inversions, for example, enforcing div B equals 0. So people still have not managed to do that. Mm-hmm. And I think that coupling all these things to basically put together inversions and these sort of reconstructions would be fantastic, but I think it's very hard. And I think actually Momo, despite me making fun of him, actually has a good point that probably neural networks could do that the easiest.
I mean, to start with, you could do experiments to try to figure out what's the error in your magnetic fields, and then just try to include it into your inversions of velocity fields to see how much does it matter. Yes. For HMI, people have done it, and they found that the measurements errors of the HMI magnetic fields, they lead to uncertainties in the flows of about 20%. But by just performing some kind of Monte Carlo runs.
I'll also remark, because one would be interested in using this from ground-based data, that when we did try to do that, the kinds of variations you got from seeing, even after correcting, really induced all kinds of spurious electric fields.
Mm-hmm. So how do you deal with it?
You can look at the literature and find out how people have dealt with it. They just haven't used ground-based magnetogram sequences for a while.
Well, that's what I know already, yes. But yeah. If we're planning to use
the other thing that always came up with this is usually the applications. You showed quite a few that had to do with the energy buildup or the helicity buildup in an active region. Having a couple of hours of observations in a day really wasn't sufficient for this kind of application.
Right.
You really wanted the round-the-clock data, even if it was every 96 minutes. It was much better to have 48 hours sampled at 96 minutes than have higher resolution, higher cadence for 2 hours and then no more for the 22 hours after that.
But I mean, with Dick's 20-kilometer resolution and super high spatial, super high cadence, we could focus on smaller scale features, and even within 2 hours, we could get nice bright points.
There's that's a new application. I think that'll be exciting.
Mm-hmm. Any other questions?
I have a very brief one. Since I didn't think about the details, but since there are curls appearing in many things, and then later we need to decurl these things, as you say. So I guess that dx and dy derivatives are sort of, we see them from the spatial distribution of the parameters. But what about d per dz? So do we assume that that's 0?
No. I mean, for GZ, you don't need DZ. But then, of course, if you're talking, for example, about horizontal currents, then you would deal with vertical derivatives as well. Now, from div B, you could get some idea of some of the div B equals 0. You could get some idea of the vertical derivatives, but in general, you're absolutely right. We have no idea about that. I guess, measurements at different levels could, from Dick's, might help you in some way. But yes,
like using few lines simultaneously.
Right, exactly. Yes, to try to get from the observational perspective these types of measurements. Yeah, if you go here, what are the main properties? The currents, the horizontal currents, Yeah, here we get EX and EX and EY from inversion, so we could get SZ. However, SX and SY, yeah, we don't get this. Yeah.
Any more questions? Comments? Okay, in that case, maybe we can call it a day. Thank you so much, Masha. I think this was really great.
Yeah, thank you, Masha.
And
Thank you.
looking forward for the next one. Yeah.
Yes.
I'm just going to remind everybody that I will be on Zoom on Monday from the noon until 2 p.m. to answer your questions regarding homework and other logistics and so on, and answer questions regarding everything that we covered in the last few weeks.
Yeah, if anybody has any
So-
questions, you feel shy, you could always email me. Thank you.
Thank you. Bye-bye.
Thank you.